In this paper, titled ImPart, Importance-Aware Delta-Sparsification for Improved Model Compression and Merging in LLMs, the authors address the growing challenge of managing multiple fine-tuned large language models. As large language models like Llama and DeepSeek continue to excel in tasks ranging from knowledge-intensive activities to complex reasoning, users often fine-tune these base models for specific tasks using customized datasets. However, storing and deploying these numerous fine-tuned models creates significant resource demands, particularly in terms of storage and computational costs. To tackle this, the paper focuses on delta compression, which targets the differences between the fine-tuned model parameters and the original base model parameters, known as delta parameters. These delta parameters capture the task-specific changes, and compressing them efficiently can greatly reduce overall resource needs. Previous methods for delta-sparsification have included randomly setting some weight entries to 0 or directly truncating singular vectors after performing singular value decomposition, or SVD. SVD is a mathematical technique that decomposes a matrix into singular values and vectors, helping to identify the most important components of the data. However, these earlier approaches have limitations. Random removal of parameters doesn't account for their importance, potentially discarding critical information as the sparsity ratio increases. Truncating singular vectors uniformly after SVD evaluates importance at too coarse a level, leading to suboptimal performance, especially on demanding tasks like mathematical reasoning or code generation. The authors introduce ImPart, a novel importance-aware delta-sparsification method that builds on SVD to dynamically adjust sparsity ratios based on the importance of different singular vectors. The key insight is that singular vectors associated with larger singular values carry more vital task-specific information. By assigning lower sparsity ratios to these important vectors and higher ratios to less important ones, ImPart ensures that crucial knowledge is preserved even at high overall sparsity levels. Here's how it works in more detail. First, the delta parameters are decomposed using SVD, resulting in a set of singular values and their corresponding singular vectors. The method then evaluates the importance of each singular vector based on the magnitude of its singular value. For vectors with larger singular values, ImPart applies a lower sparsity ratio, meaning fewer elements are set to 0, thus retaining more of the essential data. Conversely, for vectors with smaller singular values, a higher sparsity ratio is used, allowing for more aggressive compression without significantly impacting performance. To maintain accuracy after sparsification, the authors incorporate a rescaling step. This theoretically grounded adjustment ensures that the sparsified parameters still contribute effectively to the model's output, preventing any loss in performance that might arise from the changes. One of the strengths of ImPart is its versatility. It can be integrated with existing techniques for delta quantization, which reduces the precision of parameter values to save space, and for model merging, where multiple fine-tuned models are combined into a single, more efficient model. By enhancing these processes, ImPart supports higher compression ratios overall, making it a flexible tool for various applications. The paper backs up these claims with extensive experiments across different tasks and model backbones. For instance, they evaluated ImPart on the Wizard Math 13b model for mathematical reasoning on the GSM-8K dataset. Results showed that ImPart achieves a pass-at-1 accuracy of around 58 to 60% even at compression ratios up to 64, which is about twice as efficient as baseline methods like DARE and low rank. In another test with Wizard Coder 13b on the human eval dataset for code generation, ImPart maintained accuracies in the mid-50s at high compression ratios, demonstrating up to 3 times the efficiency of competitors. Additionally, for chat-related tasks using Llama 2 Chat 13b on the IF eval dataset, ImPart showed superior performance in loose prompt scenarios, achieving better scores at compression ratios of 8 to 64 compared to other methods. These experiments highlight ImPart's consistency across diverse domains, including math, code, and general conversation, underscoring its ability to handle specialized and challenging tasks without significant accuracy drops. The authors also discuss how ImPart sets new state-of-the-art results when combined with quantization and merging techniques. For example, Integrating ImPart with quantization methods allows for even finer compression by not only sparsifying but also reducing the bit precision of the remaining parameters. In model merging, it helps preserve the unique knowledge from multiple fine-tuned models, enabling the creation of a merged model that performs well across various tasks while using less resources. Overall, the experiments confirm that ImPart's adaptive approach leads to substantial improvements, with figures illustrating up to a 2x higher compression ratio at the same performance levels as baselines. This is visualized in the paper's figures, which plot compression ratios against accuracy metrics, clearly showing ImPart's edge. By focusing on the importance of singular vectors, ImPart represents a significant advancement in model compression for large language models. It not only addresses the shortcomings of prior methods but also paves the way for more efficient deployment in real-world scenarios, where resource constraints are a major barrier. The paper's contributions are particularly relevant as the field continues to grapple with the scalability of AI systems.